Hi everybody. Very good afternoon, guys. Am I audible and visible? Can you all see me and hear me? Wait, I can't see myself. Okay, yeah, you can see me. Great. Just a minute. Where's the live chat? Hore? Oh, wait a second, guys. Wait a second, huh? Yeah. Alright guys, very good afternoon and a warm welcome to Vedantu JEE English channel. This is me, your master teacher Nobomita Bhattacharjee, and as usual we are live at right 2 p.m. So what are we doing today? Today, as you can see right here, we are going to discuss states of matter and thermodynamics. Now, these two chapters, I believe together if you start to study it, these will continue for around 40 to 45 pages in your book. Now you decide you want to watch a video for 2.5 hours or 3 hours, or you want to study 40 pages, because I am going to make it simple. Yes, I am going to make it easy peasy. Biryani is tasty, clinical, clear everybody, and we are going to solve a lot of questions. Plus, you will also get your DPP. I'm going to give you 5 to 10 questions for your sake so that you can solve it on your own. So, shall we begin, everybody? Oh, thank you so much. Vanakkam. Thank you so much. Yes. So, shall we start? Shall we start? Without much further ado, let's start, because we know that time is of essence. We do not have time. We have very little time. We have around 20 days only, and yes, we are going to start. Once again, this is not working. So I have to use this. Now that you are here, do not forget to subscribe to the channel, because as you know, this channel provides all the information in English regarding your JEE, regarding EMSET, regarding BITSET, regarding your boards. Everything is done. Inorganic chemistry. Hey, I'm here. Don't worry about it. You guys only started calling me inorganic queen, no? So that'll be done. Don't worry about inorganic at all. We're going to start with physical and organic, because I believe that physical and organic is somewhere we are lagging a little bit. And inorganic, anyway, a lot of videos are there in the channel. If you just check it out, you will find it. A lot of videos are there. And those students who are new to this channel, do not forget to subscribe as well as like the session. So let's start with our first law, that is Boyle's law. Now this Boyle's law, Charles' law, or the Gay-Lussac's law. What are these laws? These laws are obviously gas laws. Yes? Why are they gas laws? Why? Because in science we have seen that everything behaves as per law, right? There is nothing that goes beyond law. If it does, then there exists another law, right? Even if it deviates from the law, then you will see that there is another law that is coming up, sneaking up and telling it, hey, you gotta change yourself, which is exactly what we will see here as well. Now, in case of Boyle's law, what we have done is we have kept constant. What is it that we have kept constant? We have kept temperature constant. Acha, now coming back to the point, before we study all of these, guys, can we also try to understand that a gas is what? A state of a matter, right? And from a very young age, we have learned that there are solid, liquid and gas, isn't it? Yes, there is solid, liquid and gas. Now, in this case, we are going to study more about gas, because they are absurd, they are random, they move around and everything. So, we have to understand them a little better. And when we try to understand them a little better, we see that there are certain things that there are certain how do I say it? Certain factors on which their movement or on which their randomness, everything depends on. And those are pressure, volume, temperature, isn't it? Yes. So when we see that these are the factors on which the behavior of the gas depends on. By looking at that, these laws came up. All right? Yes? So, in here, in the first case, temperature is kept constant. Yes? N is also constant, and we see we have arrived at an equation which is P1 V1 is equal to P2 V2. All right? So when we keep the temperature constant, yes, when we keep the temperature constant, we see that this is the equation that we come across. I will also show you the graph, so don't worry. And by the way, bacha log, what happened? Do you guys have exams right now, or are you all sleeping? Please quickly call up your friends. I see that the number of students are decreasing again and again. Quickly go call up your friends. I need the session to reach to maximum number of students so that everyone gets benefited. Yeah? Come on, guys. Go call up your friends. I had put it up on the Telegram as well. There I have also sent you the notes. So there will be certain things that I will not be talking about in the session, which is already there in the... How long does this session last? It will last around, it will last till 4:35. After that, you have your time and you can do your self-study. Acha, now we will come to Charles' law. What did Charles say? Now, because Boyle had constant temperature, what Charles did was, Charles kept the pressure constant, okay? Charles kept pressure constant. Again, once again, I'm so sorry, guys. This is all about these, this is all because of this, you know, Google slide to PPT. This always happens to us. So sorry. So when we keep P constant, we see that V1 divided by T1 is equal to V2 divided by T2. In another way, we can also say that V is equal to 1 by T, or yes, we can also say that, or directly proportional. Yes, we will use directly proportional. V is proportional to 1 by T, right? 1 by T, isn't it? That's also something that we can say. And now coming to the last law, since these guys have already taken temperature and pressure, what is left? What is left, guys? Volume is left. So Gay-Lussac's law says that if you keep volume constant and n constant, then what will we get? We will get P1 divided by T1 is equal to P2 divided by T2. Understood? Now these laws are very important. A lot of questions do come and we will be solving some questions as well. Okay? Alright, is this understood, guys? Make sense? Nonsense? Have we studied this? Have we studied this, everybody? Yes, yes, no, no. Are you toxic, friends? Board exam is going on. Acha, no problem. When are your board exams getting over, bacha log? When are your board exams getting over? Are there going to be more questions? Yes, more questions than yesterday. Plus, there will be some practice questions also. Chote bacche topics. Ah, very nice. Very nice. 23rd. Wow. And after 23rd, you have to prepare for JEE. Oh my God, that's really tough, yeah? Bachcha hona koi bachcho ka khel nahi. They say it right, no? Okay, some of you have 23rd, some of you have 21st. All right. Okay, no problem. Acha, now let's take a look at the graphs. Okay? Let's take a look at the graph. So, graphical representation of Boyle's law. When you make a graph out of the Boyle's law, you see that as you increase the pressure, the volume decreases. As you increase the pressure, the volume decreases. Hey, isn't that common sense again? You know what? I want you all to do an experiment. Try clapping like this. When you clap like this, what are you doing? With your hands, you are increasing the pressure and you are bringing it close, right? And whatever air that is here, that is right here, what is happening? See, volume reduced. I've just brought it here, right here, isn't it? So pressure increased, volume decreased. Am I right? Make sense? Just clap. Even in your exam, even if in your exam, if you're not able to understand what the scenario was, just clap. Don't clap too loud. Huh? All the other students, they will get disturbed. Anyway, now moving on to the second graph. The second graph, we can also take 1 by P and volume. Yes, and here we see that the line is absolutely straight. Yes, the line is absolutely straight. Yep. Why do we see that? Why do we see that? Take a look at it. P1 V1 is equal to P2 V2, right? Yes, because of this, we can see this here. Now, if we plot a graph, of P and PV, then what do we see? Now we already know that temperature is equal to constant, mass is equal to constant, so obviously we will see a straight line. Now all of these graph, guys, do you see that temperature constant, temperature constant, temperature constant? So what do we call it? What do you call it? Isothermal? Absolutely, yes. These are isothermal, my dear student. These are isothermal. Make sense? Yes? Easy peasy biryani is tasty, right? Right, everybody? Can I get some fire signs in the chat box so that I understand that you guys are understanding? Because I can't, if you don't tell me, I will not understand. Yes, thank you, trend cards. EPBT, amazing. Moving on. Now, if you look at the graphical representation of Charles' law, what do you see? What do you see? Are you able to see it? Or is it, anyway, I'll be sending you the this thing. Don't worry about it. So basically what we have done is, here we have drawn a graph like this, okay? So here we have temperature in Kelvin. Alright, and here we have volume. Yes. Now we see that we have graph like this, like this, okay. So here you see that there are dotted part, and these are the actual lines, okay. These are our actual lines. So we have P1, P2, P3 like this, okay. This is what it is, yeah. Now why do you have a dotted line here? We did extrapolation. Imagined and then drew the line. When we imagined and drew the line, we saw that this is basically 0, 0. That means that hypothetically we say that here the volume must be 0. Yes, here the volume must be 0. I know the graph is not visible. That's why I drew it here. This is the graph. Anyway, I'll be providing you the PDF, no? I'll provide you the PDF in the Telegram channel. That time you can watch it. But right now, just for understanding, this is our graph. Hai na? This is our graph, guys. Understanding? Yes? Getting it? Getting it or not? So this part, this is basically the lowest temperature, okay? The lowest hypothetical or imaginary temperature at which gases are supposed to occupy 0 volume. At this, gases are supposed to occupy 0 volume, okay? Yes, and this is called as absolute 0. What do we call it? We call it as absolute 0. Clear? This is our absolute 0. Which means that it is minus 273.15 degrees Celsius. If I say this, then what should be my conversion? What should be my conversion, guys? What is supposed to be my conversion? My conversion is obviously 0 degrees Celsius is equal to 273.15 Kelvin. Am I right? Is that what it is supposed to be? Is that what it is supposed to be? This is my conversion. So if at all you see in your, no. Now, minus is here, guys. This is minus. Minus 273.15 degrees Celsius. This is my absolute 0. But my conversion is 0 degrees Celsius is equal to 273.15 Kelvin. That's it. So if at all in a problem, I see that there is 0 degrees Celsius given, yes, then what will I do? I'll take it in a Kelvin, okay? I will take it in a Kelvin. Yes, I'll take it in the Kelvin measurable quantity, Kelvin unit basically. Yes. So is Charles' law clear? The graphical representation of Charles' law, is this clear, guys? Yes, is this clear? By the way, also if you want to make your calculation even easier, what you can do is instead of taking 273.15, I mean, come on. Do we want our life to be harder? Not at all. Yes, not at all. If that was the case, we would have just completed our class 10th, and maybe some of you want to be a movie star, some of you want to be a singer. You would have ran to Bombay and tried to give auditions, right? We want our life to be easier. We are studying for JEE right now. Yes, we are doing our hard work right now, but we know that our life is going to be simpler later. Nobody wants their life to be harder, guys. So if you want your calculations to be easier, then what you can do is you can just take 273 Kelvin. That's also enough. Yeah, that's also enough. Make sense? Nonsense? Easy peasy biryani is tasty. Yes? There are a lot of things that I'm saying. By the way, today's session is also going to be information heavy. Yes, Yesterday's session, there was a lot of reactions that we had to read about, a lot of derivations that we spoke about, and today's session is going to be a little information heavy, okay? All right, so I need you all to focus up like this. This is the way you focus. Focus here so that you understand everything. Chalo. Moving on to what? We are going to take a look at graphical representation of Gay-Lussac's law. Now, in case of Gay-Lussac's law, what do we see? This is isochore. Volume is constant, isn't it? This time volume is constant. So what do we get? We get isochoric graphical representation. That means that pressure versus T, pressure versus temperature graph we will plot, and we will see a line like this. We will see a line like this. That's it. Yes? That's it. Right? Okay. So these are isochore. Okay. These are isochore. What is this? This is isobar, by the way. Yes, because pressure is constant, so this is isobar, and the first one, that is Boyle's law, graphical representation of Boyle's law, the graphs were isothermal. So isothermal, isobar and isochoric. Do we understand this? Isothermal means same temperature, isobar means same pressure, and isochore means same volume. Okay? All right, clinical clear, guys? I hope so. Okay, now moving on from here, we also come to something called as Avogadro's law. Yes. So what do we do here? Yes. What do we do here? We again keep constant pressure and constant temperature. Both are constant. Okay. Both are constant. At constant P and T, what do we see? We see that V1 divided by N1 is equal to V2 divided by N2. And what did Avogadro say? Avogadro said that 1 mole of gas is equal to this many numbers. So if there are two gases or any gases, what will happen is at constant pressure and constant temperature, we will see that basically what I mean to say is equal volumes of all gases under the same condition of temperature pressure. So if I keep the temperature and pressure same condition of all gases, equal volumes will have equal number of molecules, and that's why we arrived at, remember that number, that Avogadro number, that's why we have that number. Yes, makes sense, guys? This is clear? Now see, there are so many laws, right? If I had given you some rules to be in the class, how you can be in the class, you get a pen and paper, you start writing the notes, you answer the questions that I ask you, you listen to what I am saying. Yes, then what are you? You are an ideal student. But do you listen to everything that I say? Not at all, right? Are you sitting with a pen and paper? Not at all. Some of you are probably just eating some popcorn and you're like, dozing off, right? Isn't it? So are you all ideal student? Aha! No. But maybe, just some of you have that proper, yes? Just some of you have that proper push that no, I have to consider my JEE exam to be the best. I have to appear in the JEE exam with my best mental health. I have to make sure that I know everything. But most of us are real person. And this very same way, guys, and the very same way, everybody, if a gas follows all the laws that I told you, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro law, if they follow everything, yes, then what are they? They are ideal gas. They are ideal gas. And for ideal gas, my dear student, we also have an equation. What is the equation? The equation is basically when you combine all the laws that we just spoke about, right? The equations that we saw, P1 V1 is equal to P2 V2, then we saw that V1 divided by N1 is equal to V2 N2, right? All of these, if you combine together, you will have a equation, and the equation is PV is equal to nRT. Why nRT? Why nRT? Where did this R come from? Where did this R come from? Basically what happened is we found out that PV is directly proportional to NT. Now to remove this sign, to remove this proportionally constant, remove this proportional sign, what do we need? We need a proportionality constant, and our proportionality constant becomes PV is equal to nRT. This is our proportionality constant, that means our gas constant. This is our gas constant. So let's just read it, okay? Combining all these gas laws, a simple equation can be derived which relates to PV, N and T for a gas. That is PV is equal to nRT. Do we understand this? Guys, I'm feeling a little cold. The AC is, my goodness, it's a 19 degrees Celsius. It's freezing. I'm going to die if this goes on. I'm going to die if this goes on. So cold it is, so cold. I've switched it off. In some time it should be okay. Chalo, acha. Now moving on, shall we do a question here? Let's do a question. Now that we are done with 15 degrees Celsius, dude, where are you staying? I hope you're fine. 90, oh, you should come and stay here, yeah. 19 degrees Celsius with AC on full blast, it's very cold, it's very cold. Anyway, chalo, moving on. Acha, now that we have learned a lot of laws, it's time for us to apply the laws. Yes, it's time for us to apply the laws, and we need to understand that how we can apply it in our exam, yeah. So a balloon filled with an ideal gas is taken from the surface of the sea deep to a depth of 100 meter. Sea deep to a depth of 100 meter. Alright, understanding? Yes. So a balloon that is filled with an ideal gas, not real gas, ideal gas. It has to follow all the rules, all the laws. Ideal gas from the surface of the sea, okay? Surface of the sea to a depth of 100 meter. Now what will be its volume in terms of its original volume? Pressure is going to increase a little bit, don't you think so? Or should I give you 2 minutes? You want 2 minutes to try to solve it? Chalo, let's do one thing. Try and understand what exactly is given in the question paper. I'll give you some time. Just read the question and figure out what are the things that are given to you. Read it guys. I need you all to focus up. Just read it. Yes, I'm giving you 2 minutes. Go ahead, read it. What are the things that are given to you? Does this make sense? Very good. Yes, very good. Amazing. Yes, height is given. Okay. We are also given another thing, that is the gas is ideal gas. The gas is ideal gas. That is also told to us. Yes, that is also told to us. Height is also given. So now let's see how to solve it. Chalo, let's see. Pressure at the surface, this is also given, but this was hidden in the question, guys. This was hidden. Now, when you are sitting for the JEE exam, do you think that all the question will be directly pointed towards you and you will be asked the answer? No. Whatever you are studying in NCERT, that's exactly what is coming in the exam. Only thing is, have you noticed how you take out ghee? Yeah. If you take a straight spoon like this, ghee will never come out. You will also always have to bend it a little bit to take out ghee. Same thing. JEE will not ask you questions like this, but like this they will ask you. So coming back to here, the pressure at the surface is 76 centimeter of Hg. That means 76 into 13.6 centimeter of H2O. This is our conversion. Okay, this is our conversion. Okay, so that means we will get 10.3 m of H2O. Okay. Now pressure at 100 meter depth we have to find out, okay? Pressure at 100 meter depth is equal to 100 plus 10.3 meter or 10.3 m of H2O is equal to 110.3, alright? Now what we will do, ideal gas scenario, so P1 V1 is equal to P2 V2, pressure is given to us, yes, pressure is given to us, right? So P1 V1 is equal to P2 V2. At surface, we have to find the volume, right? We have to find the volume. So what equation does work? What equation works for us the best? Of course, this P1 V1 is equal to P2 V2. So at surface, this is our at surface. P1 V1 is at surface, and we have to find P2 V2 at 100 meter depth. Yes. All right. P2 V2 at 100 meter depth. So 10.3 into V is equal to 110.3. From here we have found 110.3 into V2. So V2, if we have to calculate, we will find that it is 0.093 V, which is basically percentage. If we find out, we will do 9.3% of V. That's it. Easy peasy biryani is tasty. Yes, easy peasy biryani is tasty. That's it. That's it. That was easy, very easy, right? We got it. Moving on from here now, let's do another question. Which curve shows Charles' law? Which curve will show Charles' law? Yes, come on guys. Come on. Srinivas, this is the last revision, last revision. Bacha, I expect you to know certain concepts. Yes, I'm not teaching you from the scratch as you have seen. Otherwise, I would have also told you about forces and the different types of, van der Waals forces and all of these. So please, bacha, some of the things are already given to you in the short note in the Telegram channel. Please watch them. Yeah, watch them after the class and I hope that you will be able to understand. Okay, some of the students are saying A, some of the students are saying D, some of the students are saying B. Okay. What is the correct answer, guys? The correct answer is definitely option B, isn't it? This is the option B. Charles' law. Charles' law. Yes, what was Charles' law, everybody? Do you remember? Let me show it to you again. What was Charles' law? See? V1 by T1. That means, see, here I had told you. V and 1 by T. 1 by T happened. So that's exactly what happened in the question. See? V and 1 by T. That's it. Yes, that's it. Very easy. Now we come to something called as partial pressure. Okay, partial pressure. Why are we talking about partial pressure? Well, when we are talking about partial pressure, there is also another terms and conditions applied. The terms and condition is basically the gases do not mix with each other. The gases do not react with each other. They do not mix with each other. So when that happens, then we say that if P1, P2, P3, continue that, continue that till Pn, be the partial pressure of n gases. If you take n gases, if you have n number of gases, okay, and all of them are enclosed in a vessel. You have taken it in a vessel, okay, vessel you understand, patra, patram, vessel. You have taken it in a vessel and capital P is our total pressure. Capital P is the total pressure of the gaseous mixture. Gaseous mixture, where did it come from? Arey Baba, I just told you, no, you are taking n number of gases. So n number of gases, that means gaseous mixture, it's a gaseous mixture and they're not reacting with each other. They're just there. They're just there. All right. Yes. Now then by Dalton's law, Dalton, which Dalton? That John Dalton, yes. That John Dalton, structure of atom, we read about him. That same John Dalton, what he did was, he said that he spoke about the law of partial pressure. He says that the total pressure of this gaseous mixture which is there in the vessel, what will it be? The total pressure will be the partial pressure of all the gases that are present. Yes, everybody? Yes? Got it? Volume is directly proportional to temperature, ma'am. You have written inversely proportional. No, you're wrong. It's V divided by T1. Divided by T1. So it will be 1 by T. Yes? It will be 1 by T, not directly proportional. It's V divided by T1. Or did I write it wrong? Anyway, forget about it. We'll come back to it later. Basically, what we are doing is we are plotting a graph of V and 1 by T. Okay? 1 by T. So it will be, now if I write V is equal to 1 by T, then it will go there. Then it will be V into T. Yes, then it will be V into T. But if I write V divided by T1, then you are right. It's directly proportional. Yes, it will be directly proportional. You are right. It will be directly proportional. Yes. Okay. Acha, moving on. Partial pressure. Yes. So basically what we meant was, if we take a vessel, there are gaseous mixtures. Now the total pressure that this gaseous mixture has is basically equal to the summation of all the partial pressure, and that's exactly what is written here. P1 plus P2 plus P3 ... Pn. Okay. Now this is what we have to remember. This is what we have to remember, because we are talking about partial pressure in terms of the mole fraction. Okay? Yes? In terms of the mole fraction. Yes, everybody? Guys, don't confuse yourself so much. No, we are done with that. Now let's study this. Okay? If at all there is something, we will go back and we will try to solve it. Now try to understand this. Okay? Akash, Abhirami, everybody. Yes. Listen now. Stop worrying about it. We will check it out later. Now understand this. Okay? Otherwise, we will not be able to understand that, and everything, we will get stuck there. Yes? No confusion. The law is absolutely right, isn't it? The law is absolutely right. You forget about whatever else that is there. The law is absolutely right. That was your Charles law. Okay? Moving on from here. Now, this is what you have to remember. But the derivation is there in your book, and the derivation you will find it also. Yes. However, I do not think that right now the derivation is important, but you can do it. Okay, you can do it. Basically, it is again same thing. PV is equal to nRT. From that same formula, you can derive it like this. Okay, same formula, you can derive it like this, but this is what is important for your exam point of view. If you want to write the exam, if you want to solve the questions, then this is what you have to remember. Now, chi1 here is the mole fraction of gas. Okay, obviously, this is our mole fraction. P1 is our partial pressure of the gas. Okay, this is our partial pressure of the gas. And capital T, or this P, is basically our total pressure. This is our total pressure. Okay, yes, everybody. This formula is clear. This formula is clear. This is what is important for us in our exam. Okay, this is what is important for us in our exam. All right. Moving on from here, now what happened is we also understand something called as the rate of diffusion or effusion. Okay, the rate of diffusion, that is R, small r. And if there are two gases, both of them are under different pressure, then what will we do? What will we do? Our equation will become R1 divided by R2 is equal to V1 divided by T1 divided by V2 is divided by T2, which is equal to, my dear student, root over of D2 divided by T1, or it's equal to root over of MT divided by M1. Again, this is also something that we have to remember. Okay, this is what is something that you have to remember. Before this, there are certain things that you might want to study, but later. You do that later, or expecting that you have already studied that. Yes, now is the time that you only need this. Now is the time that you only need this. Okay, all right, everybody. Chalo. Now from here, when we move on, we come across the kinetic molecular theory. Acha, why kinetic molecular theory? Now we know that the gases are not sitting like this, no? Are they sitting and chilling like this? No, they're constantly in movement. They're moving. Randomly they are moving, right? Randomly they are moving. So kinetic molecular theory, because the molecules are moving. So kinetic. Yes, kinetic. Right, everybody? Guys, everybody, listen. I know that there are a lot of other equations also that are present, but like I said, I'm telling you the things that are important for your exam. It's a very good thing, Shiva, that you know that equation. It's a very good thing, UK Raj, that you know that thing. But like I said again, whatever is very important for you to solve the questions, these are the things that I'm talking about. If I actually have to teach you from the scratch, then one chapter will take 6 to 7 hours. You must have seen, right? Wasim sir had taken, there are sessions which are of 8 hours. Now, do you want me to waste 8 hours of your time while you are appearing for board exams as well as JEE? No, right? So, can we run a little faster? It's a very good thing. I'm so proud of you that you know it. Very good. Amazing. Thank you so much. But now calm down, okay? Listen to what I'm saying. These are the ones that are important, okay? These are the ones that are important for you. No, UK, right? No. Don't be sorry. I'm so glad that you know it. Thank you so much for knowing. You're making my work easier because you know it, okay? All I'm saying is, don't think that I'm skipping on the topic. I'm not skipping. I'm only doing that so that we can save some time, okay? And we can, we can increase the pace and we can complete it. Like I said, time is of essence. Hey, we only have 20 more days for our JEE exam, right? Yes? That's what, okay? Don't be sorry, bacha. Don't be sorry. It's fine. Acha. Now, what do we have is, so PV is equal to 1 by 3 m n naught u square, which is equal to 1 by 3 capital M u square. Now, m n naught, this term is essentially your molar mass. This m into n naught is essentially your molar mass, which is why we changed it to this. What is n naught? N naught here is Avogadro's number, alright, and u is the root mean square velocity, which we are going to learn in some time. Root mean square velocity is your u, alright, yes, okay. Now moving on from here, let's also understand, so there are different types of molecular velocities. Kinetic molecular theory, I just spoke to you about why there is kinetic molecular theory, why we have added the term kinetic, because we know that the gas molecules, they're not sitting and chilling at one place. They're constantly in movement, right? They're moving. So while they're moving, do you think that we will only take one molecule and we will like, what's your speed, bro? And do you think that the molecule will be like 10 meters per second? Will it tell you? Will it tell you? Is it possible? No. Rather than taking just one molecule, we will try to take all the molecules that are present there, and then we will try to find the velocity. We will try to find the velocity. So what are the different types of molecular velocity? Obviously, again, science hai. So we will not have just one type of, solving the problem. There are different approaches. So either we can have most probable velocity. Yes, the most probable velocity here is UMP, U, and then under script, yes, the, what do you call that? What script is it called? I have forgotten. Anyway, U, and then in the small script you write MP. What is it? What is it? Basically, let's say that you have 15 molecules. Okay, there are 15 molecules. Out of the 15 molecules, let's say one of them, subscript, thank you. Subscript and superscript, yes, subscript, absolutely right. So now let's say that one of them or two of them have a velocity of 10 meters per second. But the rest of the 13 molecules that you have, they have somewhere around 9 meters per second. Some of them have 8.9, some of them have 9.1, some of them have 9.0, some of them have 9.2, some of them have 8.8. Very close to 9, no? Yes? So that becomes our most probable velocity. That's our most probable velocity. Because we saw that majority of the molecules have that. So most probable velocity, we said that this may be the case. This may be the case. Understanding? Yes. So our most probable velocity is basically root over 2RT divided by M. We know R, we know T, we know capital M. Easy peasy biryani is tasty? Yes? Awesome. Now when we go to the next one, that is average velocity. Again, in mathematics and statistics and probability, not probability, statistics, we have learnt about that average. How do we calculate average? All the summation divided by total number. Yep. Yes. So UAV is equal to, now what we will do is 8RT divided by pi m. Alright, what do we get? 8RT, we know R, we know T, we know the pi value, and we know what is M, right? Root over of 8RT divided by pi M. Just letting you know the formula, guys. Just letting you know the formula. Or what we can do is root mean square velocity. You take the mean, you take the root over, yes, you take the mean, square it, and then you take the root over. That's your root mean square velocity, that is URM. Exactly what we just saw some time back, yes, in that kinetic molecular theory, what we saw, the same thing. So here what do we get is root over 3 PV divided by M, which is equal to root over 3 RT divided by M, obviously. And this is equal to root over 3P divided by T, okay, 3P divided by T. Now what is the relation between these three, guys? What is the relation between URMS, UAV and UMP? These three, most probable velocity, average velocity, and the root mean square velocity. What is the relation? Now we see that there are common terms. here is the common term, here is the common term, and here also we do see the common term. Yes, here also we do see the common term. So that means root over 3 is 2, root over 8 by pi. Yes, acha. MP is 2. Ha, okay. And this is 2. So root over 2. Yes, root over 3, root over 3, root over 8 by pi, and root over 2. Okay, this is our relation. This is our relation. Make sense? Make sense? Okay. All right, everybody. What is D? Here, bacha. Here. We can just solve this from here. RT by M, that we have also written it as, or V by M. Well, V by M, volume by molar mass. What is that? What is that? Volume by molar mass. Very good, Apex Legions. Yes, density. Density is equal to volume by mass, no? Same thing. Just from here we have written this. See, just use a little bit of logic and common sense. You know everything. You know everything. That's why I'm not answering all the chat box, because I feel like you can only solve your own doubts. Because right by now you have already gotten everything else, isn't it? Yes. Okay. So have we understood this? Different types of molecular velocity. Is this all clear? Is this all clear? All clear? Thank you, trend cards. Yes, is this all clear, guys? Any confusion here? Amazing. So then moving on. Okay, moving on. No doubts. Awesome. Okay. Now moving on from here. Okay. Acha, from these, okay, from these relations that we saw, from here, Maxwell-Boltzmann distribution curve came here, okay. Maxwell-Boltzmann distribution curve here. This has only come from those from all those velocities that we have studied, okay. All right. Acha, from moving on here, from here, let's try to do a question. Let's apply what we have just learned. What we have learned? You know what you have learned. I don't know. Okay. So in a container of capacity 1 liter, there are 10 to the power 23 molecules and each of mass 10 to the power minus 22 grams. So if root mean square speed is 10 to the power 5 centimeter per second, then calculate pressure of the gas. Take 2 minutes, note down what are the things that you have just found out. Note down the information from the question, guys. Note it down. Note it down, note it down. Did you find it? Yes? Okay. Let's try to solve it now. Okay. Let's try to solve it. So, we are not given the pre, right? We are not given the P. In the question, they have asked us to calculate the pressure of the gas, right? But is V given? Is V given? Yes. In a container of capacity 1 liter. 1 liter. So, we will write 10 to the power minus 3 meter cube. Makes sense? If you are asking, ma'am, how V is this 1 liter, so we will write 10 to the power minus 3 meter cube. Okay? Alright. Now, M. M is also given 10 to the power minus 25 kg, 10 to the power minus 22 grams. From here, we have converted it to kg. Yes? What are we given? In the question, it is given that, let me write that down so that it is easier for you and you don't forget. Given is that 10 to the power minus 22 grams. Okay, so we have converted this to 10 to the power minus 25 kg. Makes sense? Everybody, is this easier now? Easier to understand, everyone? Okay. What is volume that is given? Volume that is given to us is also, my dear student, 1 liter, from which we have converted it to 10 to the power minus 3 meter cube. Yes. And N is also given to us. N is given, see, 10 to the power 23 molecules. Right, everybody? 10 to the power 23 molecules. Huh? So, N is equal to 10 to the power 23. That's it. No conversion needed here. We will just simply write whatever we have got. Okay? We have written that. Now they have also told us that in a container of capacity 1 liter there are these many molecules, each of their mass is this much. Root mean square speed is. So root over u to the just above you have to draw a mark, okay, because it's a mean. So root mean square, okay, is equal to 10 to the power 5 centimeter per second. This is also given to us. So we are writing it down. Which means if we convert it, we will get 10 to the power 3 meter per second, right guys? 10 to the power 5 centimeter per second. If you convert it to meter, you will get 10 to the power 3 meter per second, correct? Easy? Okay, very simple, very easy and pretty obvious also. Now we want to remove the root. We want to remove the root sign, okay? And then what do? We will just keep the mean sign and u square. Now this value if you square it, what will you get? 10 to the power 6 meter square second square. The unit will also get squared, right guys? The unit will also get squared, it seems squared. Yes, okay. Now what do we have to do? Now we have to calculate our P value, that is pressure. So P into 10 to the power 3, that means that P1, V1 we are using. Yes, P1, V1 value we are using. No, we are using PV is equal to nRT value, okay. So what we will do is P into 10 to the power minus 3, because V is 10 to the power minus 3, which is equal to 1 by 3 into 10 to the power minus 25, okay. 10 to the power minus 25, from here m is minus 25. Then we know that n is equal to 10 to the power 23, so we are writing here n, and then finally we know that u square here is 10 to the power 6, so 10 to the power 6. Now when you calculate all of these, what do you get? P is equal to 1 by 3, 10 to the power minus 2, 10 to the power 6, 10 to the power 3. Acha, how did we get minus 2 here? How did we get minus 2? Because obviously we cancelled out this and this, right? This and this will get cancelled and you will get 10 to the power minus 2. You already have 10 to the power minus 6, and this value 10 to the power minus 3, when it has come here, you will get 10 to the power 3. So that means P is 1 by 3 into 10 to the power 7 pascals, okay? 10 to the power 7 pascals. Shiva, that's written in your book. Why will you change it from liter to 10 to the power minus 3 meter cube? It's written in your book. Please try and find it, okay? Akash says, from the formula, bacha, from the formula, we have done a lot of formula. I hope that you have observed the class from the very beginning. You will find the formulas, okay? The formulas are there. Chalo, I'll just show you it here. 1 by 3 mu square. This is our formula. Equation of kinetic molecular theory. Satish bacha, it looks like you are lagging a lot. Sweetheart, would you mind watching the basic classes first? Yeah? Please watch the basic classes once. Please. It's very difficult. It will be very difficult for me to make you explain because I see that you are the only one who is asking all of these basic questions. So I would request so that everybody gets benefited, you watch one of the basic classes that are present in this channel, okay? Just watch it. And then if you watch this, you will be able to solve the questions also. But if I go basic, then all the students who have expected to solve more previous year questions and try to speed up or try to level up with their JEE exam, it will be difficult for them. Will you please help me with that, my dear student? Yes? Will you please help me with that, my dear student? Yes? Thank you. Chalo. Moving on from here. Acha. Next question, guys. Our next question is the root mean square speed at STP. What is STP? Everybody remembers STP, standard temperature pressure. What is temperature? 273.15 Kelvin. What is pressure? 1 bar. So for the gases, okay, for the gases H2N2O2 and HBr in the order. What is their order? What is their order? Let's find out. So VRMS is directly proportional to 1 by root over m. Yes. Now we know that UH2, UN2, UO2, UHBr is basically 1 by root over 2, 1 by root over 20, 1 by root over 30, 1 by root over 81 is basically this will be our answer. Okay, this will be our answer. That means that option B is our correct answer, isn't it? Option B is our correct answer. All right. Yes, option B is our correct answer. Very good. All right. Chalo, moving on from here then. Now we come to another term called as compressibility factor. Now what is this? Another new term that's going to mess with our head. Anyway, what is compressibility? What do you mean by compressibility, guys? Common sense, compress, gases, haven't you seen? Remember the clap? Try and clap it now. Try and clap. What did you do? You compress the gases, right? Whatever gases are here right now in between these two hands, you try to compress them. That's what you did. That's what you did. So if you take a real gas, not ideal gas, a real gas, yes, the extent to which a real gas departs from the ideal behavior, it may be depicted in terms of a new function called the compressibility factor. Now we already understood that ideal gas and real gas, they are not same, just like ideal students and real student, we are all real person. We cannot behave like an ideal person, right? What is our deviation now? Now if I tell you 5 rules that these are the identification of an ideal student, let's say that I tell you that, hey, sit with a pen and paper, write down what I'm telling you. This is my second point. Third point is you listen to what I'm saying. Fourth point is I want you all to study what I have told you before that. And fifth point is sit quietly, focus here. Now what if you only listen to 3 and you don't listen to 2? Then how much are you departing? By 2 points. By 2 points you have deviated from being an ideal student. But there is also one student who have just come here to spam. He is not doing anything. How much has he deviated? 5 on 5. He is not doing all the 5 points, so he has deviated completely. Understanding the logic? The very same way, this is exactly what is written here. It's written that the extent to which a real gas departs from the ideal behavior. It was trying to go in the ideal behavior path, but it deviated from the ideal behavior path. So to what extent is it departing? That may be depicted. We can depict that. We can write that. Okay, we can understand that in terms of a new function. And what is that new function, my dear student? That's called as compressibility factor, which right now is Z is equal to PV divided by nRT. Now we need some correction, isn't it? Now we need some correction. See, I told you in the beginning that in science there are always laws that followed. Yes, laws are always followed. So if we see that laws are not being followed and there are certain differences, there are certain deviations, then we change the law. And we say that you have a new law upcoming. This is your new law. That same thing is going to happen here also. Check it out, guys. So Z is equal to PV divided by nRT. Now moving on from here, we see that when Z is equal to 1, it is ideal gas. If Z is equal to 1, then my dear student, it is our ideal gas. But if Z is not equal to 1, then it's our real gas. So if Z is not equal to 1, then that means that it can be greater than 1, it can be lesser than 1. There are 2 possibilities. If it is not equal to 1, then there are 2 possibilities, right? Either it can be more than 1 or it will be less than 1. Hai na? Hai na? Understanding, guys? Yes. Now, if Z is greater than 1, then what will we have? We will have a real gas, obviously, because Z is not equal to 1, no? Is Z equal to 1? No, I'm saying that it is greater than 1. If it is greater than 1, it's a real gas. It's not an ideal gas. Hai na? Now, here what will happen is the deviation is positive. The deviation is positive from ideal behavior. Yes? And the intermolecular repulsion, what has become here? Acha. And here what happens? You get to see intermolecular repulsion, okay? You get to see intermolecular repulsion, alright? And this gas now, it cannot be liquefied. It cannot be liquefied. Cannot be liquefied, okay? You know what, let's do one thing. Let me just edit this a little bit because I don't think you guys are going to understand it if it's written like this, hai na? Just a second. Let's try to sort it out a little bit. है ना? हाँ. Okay. Yes. Now is it understandable? Okay. So if Z is greater than 1, then what do we have? It is a real gas, obviously. Yes, it's a real gas. If it is a real gas here, then what else do we see? We also see that here, positive deviation from ideal behavior. So this was my ideal behavior, positively deviated, okay? Alright. And intermolecular repulsion has happened, okay? Intermolecular repulsion has happened. This cannot be liquefied, okay? This cannot be liquefied. Not possible. You cannot liquefy it anymore. Now here you see Z is lesser than 1. Z is lesser than 1. Yet again it will still be real gas because it's still not equal to 1. It is lesser than 1 but not equal to 1. So this is also real gas. Now this time what will happen is you will get a negative deviation from the ideal behavior. Okay, there will be a negative deviation from the ideal behavior. And that means that the intermolecular attraction is happening. There will be intermolecular attraction between them. And this can be easily liquefied. Okay, this can be easily liquefied. So these are the properties that you might have to remember. Okay? Acha. Moving on from here now, see. Remember, I just told you that now we needed what? We needed a correction. And here comes our correction. Now we are not going to write what is our ideal gas equation. It is PV is equal to nRT. Am I right? That's our ideal gas. But now we want to write it for a real gas. So what is my real gas equation? For a real gas, I'm gonna need a correction. Because I just studied that real gases don't behave like ideal gases. There is some deviation. So what are my correction? My correction is, this is my correction term and this is also my correction term. Okay. So I figured that here I am going to add a constant and here I am going to add a constant. So A and B are my constant. These are the constant characteristic of a gas. And I am going to write it as, rather than just writing PV, I am going to write it as P plus, AN square divided by V square. And I am going to write, instead of writing V, I am going to write V minus NB is equal to nRT. Alright? V minus NB is equal to nRT. Make sense? So let's understand these factors a little bit. So B is this constant. Yes, the value of B is this. Alright, and this is my volume correction. For volume correction I have added B, isn't it? And for pressure correction I have added A. So A is constant of proportionality, which depends on the nature of gas. Okay, constant of proportionality that depends on the nature of gas. So P is equal to AN square V square. That's my correction factor. And in the volume case I have added B. Alright, yes, B is the same for all gases. B is the same for all gases. However, in case of pressure correction, A is the constant of proportionality, which will depend on the nature of the gas. Is this understood, guys? Is this understood? Till here, is it all clear? Is clinic all clear till here? Yes? Awesome. Awesome. I can see that Akash is dabbing also. Very good. Thank you so much. Now we come to some more terms, that is critical temperature. Critical conditionum, remember? There was this song called Critical Conditionum. Yeah. So like that only we have some critical conditionums here. Okay. What are our critical conditionums? Critical temperature we have. So basically if Tc, how do we denote it? Array, critical temperature. No, so we will write T for temperature, and then what we will do is we will just add a chottu C so that we understand that this is our critical temperature. That's it. Easy peasy, biryani tasty. So if Tc is a maximum temperature, at which a gas can be liquefied. A gas can be liquefied. Okay? That means that the temperature above which a gas can't be liquid. So there is a particular temperature till below this the gas is liquid. Below this the gas is liquid. Yeah? Above this the gas cannot be liquid. Did I make sense? Once again guys, what do we know? See, consider ice. Ice is a solid at 0 degrees Celsius. You increase the temperature, bring it to 10 or 20 degrees Celsius, it will be liquid, and then if you keep heating it, it will be gas. So after 100 degrees Celsius, it has formed steam. So at 100 degrees Celsius, it remains a liquid. Above 100 degrees Celsius, it becomes steam. Common sense, logic behind it, understanding. Yes, the same thing, that is what I'm talking about. I'm saying that temperature above which a gas can't be liquid. Yes, all right, understanding? Exactly. So that, my dear student, is given as Tc is equal to 8A divided by 27 capital R B, small b. Then we have critical pressure. What is critical pressure? How do we denote it? We know that pressure is equal to capital P. Critical we want to explain, so a chottu c we will add. Okay. So what we will get? We will see that it is the minimum pressure that is required to cause liquefaction at Tc. What did we just mean? Do we understand this? Let me explain it. Okay. What it says is the minimum pressure. This was maximum temperature, my dear student, please note, but here it is the minimum pressure that is required to cause liquefaction. What is liquefaction? Liquefaction means to liquefy, to make it into a liquid. The minimum temperature that you need, that you require to convert the gas to liquid at critical temperature, that's my critical pressure. Which means that it becomes Pc is equal to A by 27B square. Okay. Again, all the derivation and all will be there in your book. You want to study, you want to know about it, great, amazing, you can do it. Otherwise, we will move fast. I'll just give you the formula for your quick problem solving. Okay? Now we come to critical volume. It is the volume that is occupied by 1 mole of a gas at critical temperature, critical pressure. Now if you have critical temperature and you have critical pressure, check it out. How much is the volume that the gas is occupying? That too, how much is 1 mole? 1 mole of a gas, how much volume is it occupying? That becomes my critical volume, which is equal to Vc is equal to 3B. Vc is equal to 3B. All right. Okay. Okay, these three we have understood. Great. Moving on from here. Now, what is the relation between this Tc, Pc and Vc? What is the relation between critical temperature, critical pressure and critical volume? That is basically Pc into Vc divided by Tc is equal to 3 by 8 R. Remember this. Remember this, guys. Remember this. This will be easier for you to understand a lot of questions. Okay. Now moving on from here, let's do a question, of course. So van der Waals constant A has the dimension of, what's the answer, guys? What was A? A was proportionality constant of, depends on which type of gas it was. So tell me, van der Waals constant A has the dimensions of what? Option A, mole per liter. Option B, ATM L square mole per square. Liter per mole, or is it ATM L per mole square? Different answers. Decide, guys, what is the correct answer? What's the correct answer? Decide. Okay. Let's check it out. What is the correct answer? The correct answer is, of course, option number B. It is ATM L square mole to the power -2. Yes, Apex, very good. Yes, Anamika Mukherjee. Yes, Akash. You guys are absolutely super duper right. Okay. All right. Acha, when is your bio exam, guys? When is your bio exam? Because should we wait for a while? Should we not do this session for some time and then do it again? Because the point of doing this session was to reach out to maximum students who are willing to appear for this thing. No, you want us to continue with the session. Okay, so you are telling me that those students, they will come back and watch it later? Yeah? Bio is at next month. Add. Okay. Break. Hey, no break now. It's only 3 o'clock. What? Only 1 hour has gone. No break now. No break now. I am only not tired. What are you tired? And I'm the one who is talking. Bio is on 17. Acha, chalo, theek hai. All the best, yeah. But bio is easy. Hai na? Bio is easy. Anyway, move on. Chalo, moving on. So this is how we are going to solve it if you wanted to know the solution. So basically we know that according to Van der Waals equation, P plus an square divided by v square and v minus nb is equal to nRT. Which means that P plus an square divided by v square is equal to ATM. So an square divided by v square is ATM. So A is equal to ATM into v square divided by n square, and ATM L square divided by mole square. This is L square, this is mole square. That means that ATM L square divided by mole to the power minus 2. That's it. Okay, that's it. Chalo. Next question, guys. Tell me, using Van der Waals equation, find the temperature at which 3 moles of SO2 will occupy a volume of 10 dm cube at a pressure of 1.52 MPa given A is equal to 678.88 dm cube, kPa per mole, and B is equal to 5.6 into 10 to the power minus 2 dm cube per mole. Batao. Go ahead, guys, answer. Have we found out? Uday, how are you telling me option B? But there are no options. Did you figure it out? What are the given information, everybody? What are the given information, everybody? Write that down. Anyway, chalo, let's find it out. Yes. So we know that Van der Waals equation is this. This is our Van der Waals equation, right? With the correction factor and everything. Now, R is something that we already know. It is 8.314 and this, yes. P is given to us, right? Or is it 10 dm cube? No, that's volume. MPa, pressure of 1.52, yes, that is also given to us. P is given to us. V is given to us, my dear student. Now, we just have to put the value. Just put the value here. When you put the value here, you know the value of P. So 1.52 into 10 to the power 10 to the power 3 plus 9 into 678.88, okay? 9 into 6.678.88, okay? Divided by 100. How 9? You will ask, some of you might ask, how is it 9? You tell me, guys, what is it? See what is given here, 3 moles of SO2, okay? Then what do we write? We write that 10 minus 3 into 5.6 into 10 to the power minus 2 is equal to 3 point this. Then once you solve it, yes, somebody said it, ma'am, around 620. Please give, I will try, yes. So the required temperature is 623.26 Kelvin. That's our answer. Okay? Alright, I know, big calculation, but no problem. Now you know how to do it. Okay, now you know how to do it. Once I give you the PDF, you try to do it again, okay? When I give you the PDF, try to do it once again so that you are absolutely clear on it, okay? There are also PYQs coming up now. There are also some PYQs coming up. So, here we start with our states of matter, PYQ. Shall we do it? Everybody ready? Now, I will give you the questions and you will be able to, yes. Now you will be solving it, okay? I'll give you the questions, you will be solving it. I'm not going to solve it. Chalo. So a closed tank has 2 compartments, A and B. Here is your figure also. The figure is also given. Both are filled with oxygen, and oxygen is assumed to be ideal gas, okay? Now the partition separating the two compartments is fixed and is a perfect heat insulator. If the old partition is replaced by a new partition which can slide and conduct heat but does not allow the gas to leak across, the volume in meter cube of the compartment A after the system attains equilibrium is. Chalo, try. I'll sit quietly. This is not getting switched on now. Chalo, go ahead. And as you can see, this has come in 2018 advanced. 2018 question paper, JEE advanced, you have had this question. So go ahead. Arun, you have already solved it. 2 point something. Yes. Akash, you can do it, bacha, you can do it. It's not that tough. Otherwise, I wouldn't have brought you this question because I would have known that this was advanced level. So come on. Try. Do I have your answers? Beyblade is also saying the same thing. Why is this not getting switched on now? Okay, I can see maximum answers as 2. Let's try to solve it. So, given is P1 is equal to 5 bar, form the figure as you can see. Yes, 5 bar here, see, 5 bar is written here. Alright. Yes, and here, see, V1 is equal to 1 meter cube, T1 is equal to 400 Kelvin. So, that means that our N1 is 5 divided by 400 R from PV is equal to nRT. Similarly, we will do it for the second one also. P2 is equal to 1 bar, that is again given to us in the figure. Yes, see, 1 bar, 3 meter cube and 300 Kelvin. So we will write that. Then N2 becomes 3 by 300 R. Now what we have to do is, after putting the values, we will try to put the values 1 plus x is x into 3 by 300 R is equal to 3 minus x into 5 divided by 400, or we can simplify it and we can write 1 plus x is equal to 3 minus x divided by 3 minus x into 5 divided by 4. Now at the equilibrium, we are asked to equilibrium, right? At equilibrium. So at equilibrium, the new volume of A will be 1 plus x, so the new volume of B will be 3 minus x, which is what we have done it here. Alright. Yes, which is what we have done. Alright. Yes. Now at equilibrium, due to conduction of heat, we will have, from this equation, we will find P1 divided by T1 is equal to P2 divided by T2. Also, V1 divided by N1 is equal to V2 divided by N2, or you can write it like this as well. Yes. That means when you solve this whole thing, okay, when you solve this whole thing, you will find that the new volume of A, that is 1 plus x, is equal to 11 by 9 will come 1 plus 11 by 9, that means it's 20 by 9, or it is 2.22. So yes, you all were right. Those who said that it is 2.22, 2 point something, you are absolutely right. Okay. Is this clear how to do it? Very good. Very good. Super proud of you guys. Chalo. Moving on. The diffusion coefficient of an ideal gas is proportional to its mean free path and the mean speed. The absolute temperature of an ideal gas is increased 4 times and its pressure is increased 2 times. As a result, the diffusion coefficient of this gas increases x times and the value of x is, again, 2016 advanced, everybody. Yes, try to do it. Try to do it. Come on, come on, come on, come on, come on. Let me know once you have solved it a little bit. To all the students who are liking this session, the way I have taught you, the way the questions are being provided, do not forget to hit the like button. Okay, do not forget to hit the like button, and thank you so much for already there are so many likes. Thank you so much. Chalo, let's solve it, guys. Okay, Arun Smart has answered. Very good. Anybody else who has answered? Good afternoon, Optimal Learning. How are you? How is your preparation? You can't get this, no problem, bacha. Advanced options won't be given, or it will be given. In some questions it might be given, in some there might not be, okay? It depends. Chalo. Okay, let's try to solve it. So here we have to see that diffusion coefficient is directly proportional to lambda, which is our mean free path, okay? Which is directly proportional to u mean. Alright. So that means that DC, which is diffusion coefficient, is directly proportional to lambda u mean, okay? But we know that lambda is equal to RT, okay, divided by root over 2 n naught, yes, root over 2 n naught, what is this written here, whatever, what n naught P, directly proportional to lambda, directly proportional to T by P. Now u mean, remember that formula that we have done, yes, molecular velocities to find out the molecular velocity. From there we know that mean, yes, mean is root over 8 RT divided by pi m. 8 RT divided by pi m. Yes, very good. This is sigma and rho. Yes. Now u mean is directly proportional to root over t. Yes, u mean is directly proportional to root over t. So DC is directly proportional to t to the power 3 by 2 divided by, once again here correction, okay. Now what you have done is you have one DC and you will have 2 DC, right? There will be 2 DCs, isn't it? 4 times its pressure and it's increased 2 times, right? So from here what we will do is, from here we will try to solve it like this, and as many of you have answered, it is 4. It is 4, okay? The answer is 4. No, not 1 by 4, Shiva Shankar, not 1 by 4, it will be 4. Because it's 1 by 2 multiplied with 8, no? 1 by 2 multiplied with 8, na baba? Yes? So that means that you will have to cancel it here, you will get 4. Hai na? You will get 4. No, not 1 by 4, not 1 by 4. Somewhere your calculation is a little wrong. You did ulta. Ayya. What did you do? DC1 divided by DC2 you have done. Is that what you have done? Maybe that's why. Hai na? Maybe that's why you got it ulta. Is that what you have done? Chalo, koi baat nahi. No problem. It's okay. Now you understood what you have to do. Right? Now you have to understand. Let me write this properly. Okay. All right. Moving on from here then. Next question. A closed vessel with rigid walls contains 1 mole of what? It's not given. 1 mole of uranium 238-92 air at 298 Kelvin, considering complete decay of this to plumbum 206-82. The ratio of the final pressure to the initial pressure of the system at 298 Kelvin is. Tell me. Something is wrong here. Some information is not given here, guys. How about I will give you the PDF, okay? I'll do one thing. I'll do one thing. Yes, they missed it. Don't worry. Let me do one thing. Take this as a homework question. Take this as a homework question. When I give you the PDF, I will correct this and give it to you. Okay? I will add it here. I will edit it and then I will give you the PDF. You take this as a homework question. Is that okay? Take this as a homework question. I'll edit this and then I'll give it to you. Okay? In the Telegram channel, guys. You know what the Telegram channel is, hai na? You know where the Telegram channel is, so I will edit this and I'll give it to you. Okay, move on. Let's move on. Let's move on. Let's not waste our time. Let's move on from here. If the value of Avogadro number is 6.023 into 10 to the power minus 23 per mole and the value of Boltzmann constant is given, then the number of significant digits in the calculated value of the universal gas constant is. Come on. Chalo. Yeah, I know, but PB also had to have some value, no? So don't worry, I will edit that and then give it to you. Then you solve it. Anyway, the solution is given. If you are not able to solve it, then you check it out, okay? Then you see it. I just don't want to confuse you all. So once I am done with the session, I will edit that and I'll give it to you. Okay? Solve this now. Solve this. You have already found out. Anybody else? Ooh, that's a huge variation in your answers, huh? Huge variations in your answers, guys. Anyway, let me solve it. Let me solve it for you. Okay, so universal gas constant as we know is R is equal to KNA. K is what? It's our Boltzmann constant, right? Which is given to us. And Na is our Avogadro's number. So that means that our R is equal to KNA. That means that as per the values, we will just put the values and we will see that 8.31174, which we can write it as 8.312 because 117, so 7 it will get rounded off 312, right? Now, because we know that K and Na, both of them have 4 digits only, right? Both of them have 4 significant figures. So, we will write the value of R also will be rounded off to 4 significant figures. That's it. 4 significant figures. Absolutely right. Yes, we will write it in 4 significant figures. That's it. So, so that means they are asking you an integer here, okay? They are asking you for an integer here. So, what will you write? Yes. You will not write 8.312, you will write 4 because they are asked, the question is a integer form. The question is in the integer form, so you just have to write 4. That's it. Okay, that's it. You don't have to write the value. Okay, moving on. Okay, to an evacuated vessel with a movable piston under external pressure of 1 atm, 0.1 mole of helium and 1.0 mole of an unknown compound, vapor pressure is given, are introduced. Considering the ideal gas behavior, the total volume in liter of the gases at 0 degrees Celsius is close to what? A little old question from 2011, but I believe you can do it. So once again, 2 minutes everybody. Let's try to solve it. Chalo. Come on, guys. First, write down what are the things that are given to you, then try to solve it. Today, I am not going to give you a break because we have only another chapter that we have to do. And I think we can finish another chapter and only then we can go, right? We will try to finish the class early instead of giving you a break. Are we done? Yes, Arun? Okay. Arun has given the answers. Anybody else? Okay, let's solve it. Because the external pressure is already given, that is 1 atm, yes. The gas pressure is also 1 atm, yes. And as the piston is movable, you are able to move the piston. You are able to move the piston, yes. So that means that 1 atm partial pressure due to unknown compound is 0.68, yes. Once again given value, yes. So the partial pressure of will be 1.00 minus 0.68, yes, 1.00 minus 0.68. What will we get? We will get 0.32. Now what we will do is volume is equal to nRT divided by P. When we do this, we will get 0.1 into 0.082 into 273 divided by 0.32, which is equal to 7 liters. So yes, you are absolutely right. Yes, you are absolutely right. You could do PV nRT also. Yes, PV nRT is actually the correct this thing. Okay, so you have PV nRT. That's exactly what you have done. Okay, that's exactly what you have done. Chalo, moving on from here. Now let's begin with our next chapter, that is thermodynamics. Shall we? Shall we, everybody? Are we ready? Are we ready? Everyone? Are you awake or napping? Wake up. Wake up, everybody. Wake up. Yes? Chalo. Thermodynamics. Yes, I want some fire. I want to see some fire. Because we are talking about thermodynamics. Yes. Okay. Ready. Amazing. Amazing. You know, or do all of that. Be all ready. And let's start. So in thermodynamics, the first thing that we have to understand, my dear student, is there are three terms that we talk about, that is a system surrounding a boundary. Okay. I would like to give you a very weird example, which I'm pretty sure that not somebody will give you. Have you seen in movies or in series how a sniper, you know, a sniper gun or whatever they are called as, what do? They sit with this thing, with a gun, very far away. And a lot of times in camera they show, you remember that you know, this kind of structure that you see, this kind of thing that you see, that this is where they are going to hit. Have you seen this kind of structure? Yes, this kind of lines that you must have seen. Yeah. So basically, if you can try to understand that, everything is there in the camera, but most of it is blur. Most of it is blur. Whatever they are focusing on is the only thing that matters for the sniper, right? Wherever those lines are there, that's where the sniper is going to focus on. Rest everything is also there. But they're not going to focus there. They are only focusing on that one particular point where they can shoot. And something exactly like this is these three terms, my dear student. What is system? System is, so this, whatever these snipers they are focusing on, don't you think that it is a part of the whole frame? It is a part of the whole frame. Although the whole frame has become blur, that part is the only one that you are focusing on. You can see it clearly, yes, but it is a part of the frame, right? So the very same way, can I say that system is also a part of the universe that we are interested on? The sniper is interested to shoot at that place which is focused. Yeah, makes sense? Same analogy? Great. Now these lines, they differentiate between the blur part and the focus part. Yes, these lines, they differentiate between the blur part and the focus part. Am I right, everybody? Yes. So can I call these lines to be a boundary? Yes. The very same way here also, boundary, surface that separates system from its surrounding. And everything else that is there in the frame that the sniper can see, the blur part, the focus part, all of these is what? The surrounding, the rest of the universe. The blur part is your surrounding, the rest of the universe. Yes? Understood now? Understood? So these are the three things that you have to understand, very basic to understand thermodynamics. So basically the universe, the whole universe is your system plus surrounding. If I again come back to the same example, what will I say? The frame which the sniper is able to see is basically the blur part as well as the focus part. Same thing. Same thing is what they are talking about. Moving on from here, now we also have to understand the difference between extensive and intensive properties. Okay. So these extensive properties, what do they depend upon? They depend upon the quantity of the matter that is contained in the system. What do they depend upon? They depend upon the quantity of the matter. In a system, what is the quantity of the matter that is there? That is what it depends upon. But intensive doesn't matter. It doesn't matter. They are independent of the amount. Whatever be the amount, they are going to be the same. Okay? Independent of the amount of the substance that is present in the system. Am I making sense? Are you able to understand, everybody? Extensive is additive in nature, whereas intensive is non-additive in nature. Yes? Alright? Intensive is the ratio of two extensive property is an intensive property. Yes? If you have the ratio of two extensive property, then it is going to be an intensive property. What are the examples of extensive property? Mass, volume, heat capacity, internal energy, enthalpy, entropy, Gibbs free energy. These are all extensive properties, my dear student. However, intensive properties are molar mass, molar volume, molar heat capacity, specific heat capacity, temperature, pressure, refractive index, viscosity, density, surface tension. These are all intensive properties. Make sense? Is this all clear? Do we understand this? Yes, we do. Very good. Next question, next thing, everyone. Now we also have to understand state function. Okay, now we also have to understand state function. Acha, state function and path function, let's understand this. Okay, imagine that you are told that you have to go to the school from your home. From your home, you have to go to the school. Yes? Mindy, I don't know why yesterday also I could see that your chats always come just after what I have taught you. Sweetheart, I just told you, no? These are the ones that are intensive, these are the ones that are extensive. Just gave you example, okay? Acha. Now coming to the state function and the path function. You are told that you have to go to the school from your home. It doesn't matter how you are going. You're going by train, you're going by walking, you're going by a bus, somebody is dropping you home, you are going by a cycle. Doesn't matter. Doesn't matter. It's a state function. Who cares? All we need is your presence, your attendance in the school. So that's a state function. The very same way, if the value of a physical quantity, it only depends upon the state of the system, and it does not depend upon the path by which this state has been attained. Does it matter how you are going to school? It doesn't matter. All we want is you should be in the school. That's it. That's it. The very same way, it doesn't matter here that what path has been taken. We only care about the state of the system. That's it. So what are the examples of state function? You have pressure, you have volume, you have temperature, you have internal energy, entropy and free energy. Now coming to path function. Let's say that my mom has asked me that, beta, while you are coming home, pick up some medicines, also pick up some cat food, also pick up some food for me also. Maybe pick a plate of biryani for me as well. Now what happened? My mom has basically told me that this is the path you have to follow. She told me that you have to go to the medical shop, you have to go to the pet shop, and you have to go to the biryani place so that you can bring me all of these. So my path is decided, right? My path is decided. The very same way, quantities which are dependent on the path or way the system has achieved a particular state. Now it matters how I come home. It matters. Now either I will cycle so that I can reach all the places, or I will take a bus so that I can reach all the places. Yes? Now I can't take certain options that will directly take me home. I will not be able to take that. Exactly the same way, here also the examples of path function are heat, work, heat capacities, that is molar heat capacity, specific heat capacities, and etc. Is this understood, my dear student, the state function and the path function? Do we understand the difference here? Yes? Do we understand the difference here, guys? Yes or no? Everyone, Mindy facts, now I hope that you are clear on it. Yes? Okay. Moving on from here then, now among the following, the intensive property is, now you decide, guys, tell me, is it molar conductivity, electromotive force, resistance, or is it heat capacity? You tell me. Thank you. So proud and so happy that I could help you. Bolo, bolo, bolo. Is it only A? Anant, is it only A? Check it out once more. Is it only A? Actually 2. Both this and this are the correct answer, isn't it? Both this and this are the correct answer. Yes, molar conductivity and electromotive force, both of them are going to be in intensive property. Next question, okay? Yes, next question, because these are size independent, okay? Next question. Among the following, which ones are the state function? This is a little easy. This is a little on the easier side, but you know, we are revving up the engine as we move forward with the thermodynamics chapter. We will reach where we can do better questions. Chalo. Among the following, which ones are the state function? Is it internal energy, heat capacity, expansion work, or is it molar enthalpy? Tell. Are you sure? Come on. Do we have the answer? Good. The answer is obviously internal energy and molar enthalpy. Who was it who said A and D? Very good, Arun Smart. Very good, bacha. Yes, it is A and D, both of them. Well done. Chalo. State functions are internal energy and molar enthalpy. Now, let's understand what is this internal energy. What is this internal energy? What do you think is this internal energy basically? Huh? What do you think is the internal energy, guys? We all know, right? It's written. Chalo. So basically, internal energy that is denoted by E or U, it is U kinetic plus U potential plus U electronic plus U nuclear. So the absolute value of this internal energy, you can never calculate it. The absolute value you can never calculate, okay? Yes? But what can you calculate? You can only calculate the change in the value of U. That means delta U is something that you can calculate, okay? That means that delta U is something that you can calculate for a particular process. Which means that how will I calculate delta U is equal to U final minus U initial? Obviously pretty simple, pretty easy. Why we can't calculate? Check it out, Anand. You have U kinetic, U potential, U electronic, U nuclear, and ... There are some more energies that are there. How many will you calculate? Life should be simple, no? Life cannot be hard. That is why. See, it goes on and on. There are so many more things that you have to add. Why will you do that? Why will you make your life so complicated? We will not do that. Rather, we will calculate the delta U. Okay? We will calculate the delta U. Acha. Now we come to heat capacity. Now we come to heat capacity. Hai na? What is heat capacity? The quantity of heat that is required by the system to raise the temperature of the system by 1 degree. Do you remember we have studied this in our junior classes also? Remember the heat chapter and all of these wherever we have studied in physics? Yes, we have actually completed this. Heat capacity, we learned this. Quantity of heat. Heat is what? Heat is an energy. So the amount of energy, amount of heat energy that is required by any system to just raise its temperature by 1 degree. 1 degree, that means temperature. You are increasing the degree. You are increasing the degree of hotness or coldness. Hotness here, because you are increasing, so obviously hotness, this is what you are increasing. Isn't it? So how do we give the equation for heat capacity? Ct is equal to delta Q divided by delta T. That means that we can also write it as dQ divided by dt, and its unit is joule per degree Celsius. Make sense? Easy peasy, biryani is tasty. Who, after such a long time I've said that. Anyway, moving on. Now what is molar heat capacity? Oh, obviously bro, from the term only we can understand, no, that this relates to 1 mole. Heat required, the amount of heat that is required to raise the temperature of 1 mole. 1 mole of a substance is there, and we want to increase that 1 mole of a substance temperature by 1 degree Celsius. So what is the amount of heat energy that we have to provide? That is our molar heat capacity. Easy peasy, biryani is tasty once again, which we will give it as almost similar to this. Cm is equal to delta Q divided by N. Why? Because mole has come, no? Mole has come into the picture. So that means that N into delta T, which is equal to dQ divided by N dt. And once again, the unit here will be J per mole Kelvin per Kelvin, okay? Joule per mole per Kelvin. Obviously, dq is what? dq is what? This is joule, and this here is per mole and Kelvin. So that means joule per mole per Kelvin. Yes, easy, very easy. Chalo, moving on from here. Now let's understand what is heat and what is work. What is heat and what is work? Once again, very simple, very easy, something that we have learned when we were chottu. What did we learn? We learned that when the energy transfer between the system and surrounding takes place because of temperature difference. Let me draw one drawing for you, okay? Let me draw one drawing for you. Let's say that this is what I'm drawing. This is my system and this is my surrounding, okay? Now, when this happens, okay, when Q is getting transferred here, then what is happening? What is happening here? That means that the system has more heat. System has more heat. That is why it is transferring the heat to the surrounding, right? That is why it is giving away the heat to the surrounding. Am I right? Yes, everybody. Yes, very good. Now, if I say that, check it out. Now, if I say that from the surrounding Q is getting transferred, then what is happening? That means that the surrounding has more heat. Easy? Easy? Very easy? Very easy? From the picture also you can understand, from this also you can understand. That's what exactly we are saying, right? When the energy transfer between a system and a surrounding takes place, why does it take place? Because there is a temperature difference, and we know that heat energy always flows from somewhere there is more energy to lesser energy. That means a body that is hot will transfer it to a body that is cold, right? Moving on, same thing with work also. Any energy transfer which is not heat or which is not because of temperature difference is called work. That means there is volume that is related here. That means volume is applicable here for work. Yes. So when volume increases, volume decreases. Yes. That is your work done. That's basically your work done. Because we are clearly saying that any energy transfer which is not heat or not because of temperature. So that means if I apply pressure and my volume changes, that is work done? That is work done? Absolutely yes. Absolutely correct. What you thought is absolutely right. Yes, that's the correct thing. So moving on from here, now PV work let's understand. Okay, what is PV work? Let's understand. Check it out here. So we are saying that this is my A, that is area obviously. This much part is our D, and from here to here it is L, and like this part is X. So this part, like from here to here, it is L minus X obviously, and P is the pressure that I am applying. This is my piston. I am trying to move it. Yes, I am trying to move it. So for a small displacement, very small displacement guys, the piston only moved a little. Very small displacement dx. Because of what? Force. I have applied some force. Right, I have applied some force, so the displacement is very chotu dx. Yes. Now what is the work done on the system? What is the work done here? Okay, for the work done, we know that it will be dw is equal to f dx, f dot dx. Now what is my f? What is my f? From a very age-old formula, we know that force is equal to pressure into area, or pressure is equal to force divided by area. So that means that we can write f is equal to pa. If I write that, then I also know that I can write dw is equal to pa dot dx. Yes, pa dot dx, I can write this also. If I write this, then what do I know? I will know, I also know that v is equal to L minus x, L minus x and multiplied with a. That means that dv is equal to minus a dot dx. Because dw, that means that dw is equal to minus p external dv. I'll write it down here. Okay, this is it. This is it. So that means that if I want the whole work, I will have to do minus integration v1 to v2 p external dv. That's it. Is this clear, guys? Is this clear? Yes? Is this clear? Got it? Got it, guys? Yes. Okay. Moving on from here. See, this is what, okay, now these are the sign convention. Sign convention in chemistry, not talking about physics, sign convention in chemistry. If the system absorbs heat, then it will be plus Q. And if the system gives away heat, it releases heat, then it is going to be minus Q. Okay? If the work done is on the system, then it will be plus Q. Understand it? Imagine that I'm hungry and I'm only eating. Someone is feeding me. Then what is happening? The work is done on me. I'll be like, whoa, right? But if I start my activity and if I keep running, then work is done by my body. Then what am I doing? I'm losing out the energy. So work done by the system. I am the one who is doing the work. It's done by me. It is done by me. So what is happening? Minus W. Makes sense? Yes? Good example to understand. Good example to remember it. Yes? Okay. Also, I'm very hungry. That's why this example came up. Anyway, now let's come to the first law of thermodynamics. My dear student, can somebody tell me what is the first law of thermodynamics? Can somebody tell me what is the first law of thermodynamics? I want to see, guys. I want to see. Who can tell me what is first law of thermodynamics? Come on. Energy can neither be, oh, just what happened? What is the first law of thermodynamics? Energy can neither be created nor destroyed. It can simply be converted from one form to another. Yes, energy can, Mitra, that you have to see in physics, right? Energy can neither be created nor be destroyed. It can only get converted from one form to another. And this whole sentence that we are speaking about, mathematically we can write it as U2 is equal to U1 plus Q plus W. Which means that delta U, once again, what do we want? We want the change in U, right? So delta U is equal to U2 minus U1, final minus initial, right? Which is equal to Q plus W. What is U1? U1 is the internal energy at initial state. What is U2? U2 is the internal energy at final state. Yes. And Q is the amount of heat that is given to it, and W is the amount of work is done on it. Aditya, that is the different law. That is a different law. No, you're right. Yeah, you're right. Absolutely right. Very good. Chalo, moving on. Now here is a question for you, and the question is, my dear student, yes Aditya, you're right, yes, energy on an isolated system is always conserved. Okay, I was just messing with you, bacha. Yes. Acha, so a system undergoes a process which absorbed 0.5 kilojoule of heat and undergoing an expansion against external pressure of 1 atm. During the process, change in internal energy is 300 joule. Then predict the change in volume in liters. Batao. Come on, guys. Ajay, yes. So what's the answer? What's the answer? Chalo, let's figure it out. Our answer is option 2. A system undergoes a process which absorbed 0.5 kilojoule of heat and undergoing an expansion against external pressure of 1. This is how we are going to solve it. So delta U is equal to Q plus W. We have just learned. That means Q minus, what is W? W is P external. Yes, V2 minus V1. Delta V. So 300 is equal to, 300 is given to us. So 300 is equal to 500 minus 1 delta V into 100. Then delta V we can find out 500 minus 300 divided by 100 is equal to 2 liter. That's it. Okay, that's it. Moving on from here, reversible and non-reversible processes. Reversible and irreversible processes. Let's talk about that. Acha, what is reversible process? Basically, reversible process is one such a reaction where you can change the direction of the reaction. Yes, you can change the direction of the reaction by an infinitesimal change to the system or surrounding. Basically, we also want to say that it is so slow that a little change can change the direction of the process. Yes, it can change the direction of the process. All right. Yes. And what is irreversible? Where you cannot do this. Where you cannot do this. So, in case of reversible reaction, we can write that P external is equal to P internal plus minus dP. It's a very small infinitesimal change, very small change. So, dP internal. Right? Right? Hey, can you guys see me? I think there was a glitch for some time. Yes, Arun. Yes, absolutely right. Can you guys see me? Is it continuing? Okay, there was a glitch for a while. Huh. Chalo, theek hai. All right, theek hai then. Moving on from here then, irreversible process, I just told you, forget about this. Huh. Now let's talk about enthalpy. What is enthalpy? Enthalpy, my dear student, is basically the measure of the total energy of thermodynamic system. Total energy of a thermodynamic system. If you have a thermodynamic system, what is the total energy? That, my dear student, is my enthalpy. So, enthalpy of a system is defined as H is equal to U plus PV. So, if I know H, then if I want to find out dH, that means it will be equal to du plus dPV, where H is the enthalpy of the system, U is the internal energy of the system, what is the PP is the pressure at the boundary of the system and its environment, and V is volume of the system. Obviously, we know all of these terms, right? We know all of these terms, okay? All right? Yes. Moving on from here then, this is not coming here now. Anyway. So, our enthalpy of system is defined as this H is equal to U plus PV. So, this is something that we have just learned. Now, if I take constant pressure, then what will be my heat capacity, my dear student? My heat capacity will be QP is equal to NCP delta T. Yes, these are the ones that you have to remember, okay? These are the formulas that you have to remember. So, the value is equal to the change in enthalpy, that is QP is equal to NCP delta T, which is equal to delta H. And similarly, if I take constant volume V, then what will I have? I will have QV is equal to NCV delta T. Yes, I will have NCV delta T. And this value is equal to the change in internal energy. So, that means that my QV is equal to NCV delta T is equal to delta U. Yes? Is that right? Is that right? So, here I get heat capacity, change in enthalpy. All right? Yes? And then we have taken constant volume, and then we have found out the change in internal energy as well. Yes? Are we clear with this? Okay. So, moving on from here then, once again it went there. Hey, okay. A question for you guys, a question. The question is, 1 mole of a non-ideal gas undergoes a change of state from 1.0 atm, 3.0 liter, 200 Kelvin to pressure, volume, temperature is given with a change in internal energy, and the internal energy change is also given to you. Okay, delta U is equal to 40 LATM. The change in enthalpy of the process in LATM is, chalo, try to solve this. Let's see. Try to solve it, guys. Okay, okay. Arun, very fast you have answered it. Well done. Ajay has also answered. Chalo, let's see how to solve it then. Okay, let's see how to solve it. So, our answer will be, okay. Our answer is yes, option B, but how? Now, both P and V are changing. right? Both P and V are changing. That means delta H is equal to delta U plus delta PV. So delta U plus P2 V2 minus P1 V1, that's how we can take it. Yes, that's how we will take it. So delta H is equal to 40 plus 20 was given to us. Yes, 20. I mean, that's how we will calculate. No, P2 V2. P2 V2 is what? 5 and 4. So 5 4s are 20. And then 1 into 3. So 20 minus 3, which is equal to 57 L ATM. Good. Now let's understand the isochoric process. As I had already told you, bacha, isochoric means volume will be constant. Yes, whenever we use the word isochoric, that means that it is what? It is volume is constant. So if volume is only constant, then dV will be obviously 0. Yes, dV will be obviously 0. Now W will also be equal to 0. Yes, W will also be 0 because remember what was work? What was work? We have studied that volume, pressure. So dV is equal to 0, W is also 0. Now from the first law of thermodynamics, we can say that delta U is equal to QV. Yep. Yes. That means heat exchanged at constant volume. QV is what? Heat exchanged at constant volume. Am I right? Now for isochoric process, if we take a look at this graph, then this is my V, this is my V1 and this is my graph. This is my graph. Riya, you can watch it, bacha, if you want to. Yeah, you can watch it if you want to because the syllabus is almost the same. Yeah. What is isobar? Isobar is pressure same, okay? Pressure same. Pressure is constant. No, I will not be teaching a batch, bacha. I will only be teaching on YouTube, okay? I will only be teaching on YouTube, not on batches. Chalo, moving on. Now, let's talk about isobaric process. What is isobaric process? So, P gas, that means pressure of the gas is constant. If pressure of the gas is constant, so since pressure of gas is defined during whole of the process and hence the pressure must be reversible. Pressure must be reversible. Which means that dW is equal to minus P external dV. Now I can also write it as minus P gas dV, which I can write it as minus P gas integrated from VI initial to V final dV, which means that my work W will be equal to P of VF minus VI. Am I right? Am I right, everybody? Does this make sense to you guys? Does this make sense to you guys? Yes or no? Yes or no? Yes or no? Yes. Okay. Moving on from here then, isothermal process, okay? So T is equal to constant throughout the process. Now this time what are we doing? Isothermal, that means thermal, temperature we are keeping it constant. That means our dt is equal to 0. Obviously constant hai, dt is equal to 0. Now for the expansion of an ideal gas, now what are we doing? We are taking expansion of an ideal gas. What will it be? Delta U is equal to NCV delta E, which means delta H is equal to NCP delta T. Delta U and delta H will also be equal to 0. Yes? Yes? Isn't it? Why? 0 here and 0 here. What will it be? Delta U and delta H will also be equal to 0. Makes sense? Makes sense, everyone? Yes? Makes sense? Yes, these are all thermodynamic process. Yes? So no problem, Ritik. You can definitely come here. Here I will teach you. Pakka promise. Yes? Here I will be teaching you. Don't worry. Ole, thank you so much. Thank you so much. Thank you so much, Riya. Okay. Acha, moving on from here then. Now, talking about isothermal process, we are continuing with it. So, work done in reversible isothermal process, beta, please try and remember this, okay? Try and remember this. This is very, very important. Work done reversible is equal to minus 2.303 RT log of V2 by V1, and W in reversible is minus 2.303 RT, same thing, but just P1, P2, and this is V2, V1, okay? You have to remember this. Alright, hi Navina, hello bacha. So work done in irreversible isothermal process will be CW irreversible is equal to minus P external V2 minus V1 that we have just seen some time back, isn't it? We have just seen it some time back. Moving on from here, I suppose we are almost coming to the end of the session, or are we? No, not yet. Wow, what a big chapter here. Anyway, acha. So now there is in an adiabatic process. Now we are going to talk about another term, that is adiabatic process. What happens in an adiabatic process? There is no heat change between the system and the surrounding. Nothing. Nothing. Yes? Yes? So Q is equal to 0. Now from the first law of thermodynamics, what do we know? Delta U is equal to Q plus W. If I know this, delta U is equal to Q plus W, now delta U is equal to W, yes, because there is no heat exchange between system and surrounding. Is it possible that my W is negative? When will W be negative? When my delta U is lesser than 0, when my delta T is lesser than 0, and T2 is less than T1. Yes? Temperature decreases, so cooling occurs here. Alright? There is another possibility, that is W is positive when delta U is greater than 0. T2 is greater than T1. If T2 is greater than T1, then what is happening? Temperature is increasing. Heating is happening here. Heating is happening here. Yes, bacha? Yes. Make sense? Okay. Moving on from here then, now work done in adiabatic process, let's talk about that also. So reversible adiabatic process, okay, what is reversible adiabatic process? Reversible I have explained, adiabatic also I have explained. So work done will be equal to P2 V2 minus P1 V1 gamma minus 1, try remember this also, important, okay. And for irreversible adiabatic process, okay, for irreversible adiabatic process, what do we know? We know that W is equal to NCV T2 minus T1, which is equal to the same formula, guys. That the same, okay. From the very beginning, NR T2 minus T1 gamma minus 1 is equal to same thing, P2 V2 minus P1 V1 divided by gamma minus 1. Exactly the same thing, okay. So basically, whatever you have learned in the very beginning of the chapter, that is what is getting repeated again and again, okay. It's just simple chotu-motu derivations here and there, okay, or deviations here and there. Now, here is a question for you. In figure A and B are two adiabatic curves for two different gases. Then A and B corresponds to AR and HE respectively, HE and hydrogen respectively, oxygen and hydrogen respectively, or is it hydrogen and helium respectively? Chal. You tell me, guys. I'll give you some time so that you can solve it. Or should I answer? Should I answer? Very good. I can see two answers here. C, B, somebody also say A and D. Then all of the options will get covered. Acha. Chalo, let's answer. What's the answer? The answer is option B. Why? Because the slope here was minus gamma, and if slope of A is greater than slope of B, so gamma of A is also greater than gamma of B. So that means that A is helium and B is hydrogen, okay? Alright, moving on from here. Next question is 5 mole of an ideal gas expand isothermally and irreversible from a pressure of 10 atm to 1 atm against a constant external pressure of 1 atm, and 1 atm, W is irreversible at 300 Kelvin. Calculate. All right, I see some options, B, C, all of that. Let's do this. The correct answer is option B, my dear student. And how are we solving it? So we will do integration dw and then again minus integration P external dV from the formula. Yes. Now, work irreversible, right? So irreversible, when it is irreversible, then it becomes minus Pxt. In square bracket, we will write nRT minus P2 minus nRT by P2 minus nRT divided by P1. So work irreversible will be equal to, P external is given to us, yes, 1 atm, so minus 1. Then what is given to us? See, what is given to us? 5 moles, so we are going to write 5. R, we already know that it is 8.314 into 300 because 300 Kelvin is also given. Multiplied with 1 minus 1 by 10. Yes, why did we not write the P2? Because P2 we know that it is 1. So 1 minus 1 by 10. Yes. Now when you solve it, okay. Now when you solve it, what do you see? What do you, what do you write? The answer that you will get is this. The answer that you will get is minus 11.224 kilojoule, okay, 224 kilojoule, minus 11.224 kilojoule. Chalo, moving on. Next question, guys. The next question, guys, are a gas CVM is equal to 5 by 2R behaving ideally was allowed to expand irreversibly and adiabatically from 1 liter to 32 liter. Its initial temperature was 327 degrees Celsius and the molar enthalpy change in joule per mole for the process is, you tell me. Go ahead, guys. Come on. Yeah, definitely. Are we done? Okay, I see some answer. Chalo, let's try to see how to solve it, okay? Yes. Now we know that, see, what is given to us? A gas that is behaving ideally, yes? And it was allowed to expand, reversibly and adiabatically from 1 liter to 3 liter, yes? 1 liter to 32 liter. So volume, we got the volume, yes? Initial temperature is also something that we know that is 327 degrees Celsius. And now we want to find out the molar enthalpy change, okay? So T2 by T1 is equal to V1 by V2. Yep. All right. And then here to the power gamma minus 1 will be there. Gamma minus 1 will be there. So T2 is equal to T1. I mean, what we will do is we will try to take the T1 here, okay? We will try to cross multiply T1. And then we know that 1 by 32. So gamma is also given somewhere. From here, we can find that it is 7 by 5 minus 1. So, here, because T1, 600 divided by 1 by 2 to the power 5, that's what we can write for 32. For 32, I can write 2 to the power 5 and then I can write it as 2 by 5. Yes, I can write it as 2 by 5. That means that 600 into 0.5 square is equal to 150 Kelvin. And if I have 150 Kelvin, then that means that delta Hm is equal to 7 by 2R into 150 minus 600 will be equal to minus 1575R. Am I right? Am I right? Yes? It'll be equal to this? Yes? Very good. Chalo. Moving on from here then, match the column. Finally, one easy question. Tell me. A process actually all of them are easy. All of them were easy, right? I could see that all of you were solving, so none of them were very tough. But anyway, I will be giving you some daily practice paper, so I will see. No problem, Luxury Hitler. You know what? You can watch it from the beginning, yeah? I've taken states of matter as well as thermodynamics, so please watch it so that everything is clear for you. So a process carried out infinitesimally slowly, which one is it? I've told you this. A process in which no heat enters or leaves the system, you know which one is it? A process carried out at constant temperature and cyclic process. Oh, what is it, guys? What is it? Acha, very good. This was absolutely easy. I mean, super easy. What do we know? A process carried out at infinitesimally slow is obviously reversible. Changing the color of the pen. Obviously, this is reversible. I've just told you. A process in which no heat enters or leaves the system, obviously adiabatic. A process that is carried out at constant temperature, of course, isothermal. Could it get any more easier? And finally, a cyclic process is obviously, this is Q, delta E is equal to 0, delta H is equal to 0. Yes? Alright? Okay. Moving on then. Another match the column, guys. Reversible isothermal expansion of an ideal gas. What is the formula? Reversible adiabatic compression of an ideal gas. What is the formula? Irreversible adiabatic expansion of an ideal gas and irreversible isothermal compression of an ideal gas. Batao. Arun, I'm not very sure if this is a PYQ or not because like I said, there is Bihu ma'am who makes the content. So I'm guessing she must have taken it from a PYQ. Anyway, we will be doing a PYQ in some time, okay? Yes, match the following does come to exam. It does. It does. Why do you think I'm doing it? Not doing it only to waste your time, yeah. It does come in the exam. Chalo, batao. Are we done? Let's see the answer. The answer, my dear student, is of course C, A. Reversible isothermal expansion of an ideal gas. It means that it will be W is equal to, yes, it is P, right? W is equal to minus 2.303 nRT log V2 V1. Remember, I showed it to you. Also, reversible isothermal expansion of an ideal gas, that also means that delta H is equal to 0. Yes, it also means that delta H is equal to 0. Now, reversible adiabatic compression of an ideal gas. What is adiabatic compression of an ideal gas? It will be PV, gamma is equal to constant. And that also means that it will be W is equal to NR divided by gamma minus 1, T2 minus T1. Yes. Now, if I take irreversible adiabatic expansion of an ideal gas, that will be R. That is W is equal to NR divided by gamma minus 1, T2 minus T1. And irreversible isothermal compression of an ideal gas will be delta H is equal to 0. This is what it is, okay? This is what it is. Chalo, moving on from here. These are all the things that are given to you. You already know it. See? Same thing. PV gamma is equal to constant and W will be equal to this. Yes, for reversible adiabatic compression of a gas. Irreversible adiabatic compression of a gas, same thing. Yes, same thing. Chalo. Moving on from here. Now, 1 mole of an ideal gas, this is repeated, isn't it? Is this repeated? No, the values are repeated, but I guess you can do it. 1 mole of an ideal gas, CVM is equal to 5 by 2R at 300 Kelvin, and 5 atm is expanded adiabatically to a final pressure of 2 atm against a constant pressure of 2 atm. Final temperature of the gas is. Go ahead, guys. Let us know. Final temperature of the gas. Alright, let's check out the answer. Our answer is option C. How did we solve it? Okay, How many are there? There are some more questions. You guys only told me that, ma'am, we should bring more questions. So I got you more questions. Now you're complaining. See? Not nice. Anyway, Q is equal to 0. So delta U is equal to W. Now NCVM, that was already given to us. T2 minus T1 is equal to minus P external. Same form, that old age formula that we have been using. We'll use that formula. So CVM will be equal to T2 minus T1. And then we will write P external. R we have introduced. So T1 by P1 minus T2 by P2, we have taken this R outside. And then 5 by 2, that was given to us, CVM, it was given to us, isn't it? Yes. So 5 by 2 R, T2 minus 300 is equal to 2 into R, 300 by 5, doing all of these. T2 we will find out to be this much, okay? T2 we will, I don't have note, no problem, bacha, you can do it there, okay? You can do it later, no problem. Moving on to the next question. Acha, now we also have to talk about entropy. Oh, the chapter is not yet over. I was also in the delusion that the chapter is over, but no. Is it okay? You can see, but I doubt you will be able to understand anything, because right now what I'm doing is I'm doing advanced JEE, advanced JEE course, just so that your preparation is faster. So I would suggest you can watch it, but you watch it from the beginning, okay, the basics, okay. Now what is entropy? Entropy is obviously the measure of randomness or disorder of the system, okay. It's the randomness or disorder of the system, right? Yes. So mathematically, how do we explain randomness, or how do we explain the disorder? We will explain it as integration of ds. Integration of ds is equal to 1 by t, and then again integration, yes, we will have dou q reversible. So delta S is equal to q reversible divided by t. That's our entropy formula. That's our entropy formula, okay, mathematically. Now when we move on, we understand that there are also spontaneity in terms of entropy change. What do we have? We have spontaneity in terms of entropy change. Yes. Which means that spontaneous. When is it spontaneous? It can be either spontaneous or it can be non-spontaneous. So what is spontaneous, my dear student? Is it delta S total? Delta S total will be equal to delta S plus system plus delta S surrounding. When that is greater than 0, spontaneous. That's what you get. When do you get spontaneous? When delta S of the system plus delta S of the surrounding together is greater than 0 is your spontaneous, okay. And when is it non-spontaneous? Well, obviously when it is lesser than 0, that's when you are getting non-spontaneous. Am I right? Yes. That's what it is. Great. Moving on from here. Now calculation of delta S surrounding. Now as the surrounding of is an infinite heat reservoir, right? What do we consider? We consider that the surrounding is an infinite heat reservoir, and the hence no amount of heat is given to the surrounding. What am I reading? Hence, amount of heat given to the surrounding can cause a turbulence in it. Okay, try to understand this way. Yes, that have you noticed that if you have a big pond, you have a big pond or you have a big lake, in that even one drop of water can cause waves, right? One drop of water can also cause waves, but I already know that there is a lot of amount of water in it. The very same way, if I consider that there is infinite heat reservoir, a little amount of heat that is given to the surrounding can also cause turbulence. There will be waves, right? Hence, all the exchange with the surroundings, they are considered to be reversible. So we consider all of it to be reversible. Consider, the word is consider. It doesn't exist. Anyway, so delta S surrounding is basically integration dq surrounding divided by t, right? Okay. So for surrounding, t is constant. For the surrounding, t is constant, right? That means that delta S surrounding, once again, here also we have this thing, here also we have a slight problem. Let us just a second. I have to fix it, otherwise when I give you the slide also it will remain like this only. I hope it's correct now. Ooh, sorry. Extremely sorry, guys. Extremely sorry, huh? Just a minute. Just a minute. Yeah. Now it's fine. Okay. So that means, as I was telling, so for surrounding T is constant, that means delta S surrounding. We are figuring out delta S surrounding, which is equal to 1 by T. And then we will integrate obviously dq surrounding, which is equal to q surrounding divided by T. Now we know that law of conservation of energy, that means q surrounding has to be equal to minus q system. Yes, right? So that means that delta S surrounding will be equal to minus q system divided by T, because we know this. If q surrounding is divided by T, then what do we have to do? We know that q surrounding is equal to minus q system. That means that just by adding a negative sign, we can also figure it out here this way, right? We can also figure it out here this way. Is this clear? Is this clear, everybody? Great. Moving on from here, now we see that calculation of delta S system. We just calculated for delta S surrounding, now for system. So delta S system, once again, this is a little this thing. Let me write it by hand only, I guess. I think that's better. Isn't it? I think that's better. There are certain difficulties here, as you can see. Chalo, I will write it. For delta S system, okay, for delta S system, what do we have? We have two states. We have state 1 and we have state B, okay. We have state 1 and state B. So if I write it down, then I will write it down. Check it out. Let me write it with yellow. Hai na? We have state A here and then we have state B here. Okay. Here I can write delta S reversible and here I can write delta S irreversible. Okay, this is what I want to say. Okay. Now, as S is a state function, then delta S will not depend on path. Here, S is a state function. If it is a state function, we have already read that it will not depend on path. Yes, state function always depends on from where it is beginning to where it is ending. It doesn't matter on which path you have taken. So obviously it will not depend on path. That means that my delta S irreversible will be equal to delta S reversible. Yes, I just told you. It's not a path function. It's a state function. So delta S, you just have to integrate from A to B dq of dq reversible divided by T reversible path. That's it. That's it. Okay. And moving on from here, my dear student, now the second law of thermodynamics is where we come. And the second law states that the entropy of the universe increases in a spontaneous process. And it remains unchanged in an equilibrium process. So if you have an equilibrium process, it will remain unchanged. But the entropy of the universe is increasing in a spontaneous process. And we know what is spontaneous process. Delta S system plus delta S surrounding is greater than 0. So mathematically, my spontaneous process is exactly what I just told you. Delta S universe is equal to delta S system plus delta S surrounding greater than 0. But at equilibrium process, what will happen? Delta S universe is equal to delta S system plus delta S surrounding is equal to 0. Here it is greater than 0. Here it is equal to 0. Understanding, guys? Do I make sense? Do I make sense? We are almost done, huh? Almost done. Now we are just going to solve some questions and we'll be done. Acha. Now, entropy change for an ideal gas in a thermodynamic process. What it can be? From the first law, we already know that dq is equal to du plus pdv. So, ds will also be equal to, we have just figured it out, dq reversible divided by t, which means that it is du by t plus pdv divided by t. But for ideal gas, we know that ds of a system is equal to ncv dt divided by t plus nr by v dv. From the previous formula again, remember we figured this out also? Yes. Therefore, du is equal to, because du is equal to ncv dt, so we can put this here. So what will the integration give us? We will have to integrate. Once we integrate, we will know that delta S equal to ncv ln of t2 by t1 plus nr ln of v2 by v1. Huh? What did I say? Delta is equal to ncv ln t2 by t1 plus nr ln v2 by v1. Okay. So the general expression, this is what you have to remember now. This is what you have to remember now. Very important, guys, very important. Please note it down in your copy. Yes, or wherever you can. So delta S is equal to ncv ln t2 by t1 plus nr ln v2 by v1, which is equal to ncp ln t2 by t1 plus nr ln p1 by p2. Now, here is something interesting that we are going to do now. Here is something interesting. What are we going to do? Now, for isothermal process, reversible and irreversible isothermal expansion and contraction of an ideal gas, see, isothermal process, right? Isothermal process, check it out. Same formula, T2 by T1, gone. That whole term, check it out. So, what will be our formula? Our formula is here, nR ln V2 by V1. Once again, check it out. See, nR ln V2 by V1. Yes, this is our formula. This is our formula. Make sense? Yes, makes sense. And for surrounding, delta surrounding is equal to minus delta S system, which also we have figured it out for reversible process. So, delta S surrounding is equal to Q surrounding divided by T. This is for irreversible process. This is for irreversible process. Okay. Alright, guys. Chalo. Moving on from here now. Entropy change for an ideal gas in thermodynamic process. We are continuing with this. So, isobaric process. For isobaric process, what will happen? Pressure is same. So, delta U is equal to Cv delta T. Now, delta H will be equal to what? Cp delta T, which is equal to Qp. Of course, again we know this. So, delta S system is equal to Ncp ln of T2 by T1. Yes. And for surrounding, it will be delta S surrounding is equal to minus delta S system. Once again, for reversible, we have just some time back figured it out. Same way, for irreversible, what will happen? Delta S surrounding is equal to Q surrounding divided by T. Okay? Alright? Getting it, my dear student? Where is the chat? Where did the chat go? Huh. Yes. Okay. We have understood this also. Now, moving on from here. Yes. Isochoric process. Obviously, one last thing that we have to see is, okay, one last thing is isochoric process. So, delta U is equal to Cv delta T, which is equal to Qv. So, delta H is equal to Cp delta T. That means that delta S system is equal to Ncv ln T2 by T1. Again, that same formula, that long formula that I give you. Yes, you just have to chuck few parts and that's what you will get. For surroundings, same thing. And for irreversible process, same thing as we have just done some time back. Chalo, moving on from here, adiabatic process. Adiabatic process, delta U is equal to Cv delta T and delta H is equal to Cp delta T. Yes, guys? Yes? Now, delta S system, once again, for irreversible process, guys, for irreversible process, Ncv ln T2 by T1 plus nR ln V2 by V1. Now, delta S system is equal to 0 for reversible adiabatic compression and expansion. For surrounding, for irreversible, this is what it is. Remember that this almost remains same everywhere, okay? Yes? Now, questions. Ready? Questions? So, when 2 mole of an ideal gas is heated, okay, Cpm is equal to 5 by 2R from 300 Kelvin to 600 Kelvin at constant pressure. The change in entropy of gas is what? Batao. Hey, luxury Hitler, what question are you asking? even if it is state question, even if it is a state function, don't you think that we will still have to figure it out for isochoric, isothermal and all of that? That we will have to know. That we will have to know. Chalo, let's do this fast now. Let's do this fast. We don't want to. Very good. Option C is the correct answer. 5R ln of t. Yes, 5R ln of t, because that is as it is written, delta S is equal to NCPM ln T2 by T1, which means that it is 2 into 5 by 2. R ln 600 by 300. Solve it. You will get 5R ln 2. Okay. All right. Maybe you can, Haris. I mean, if you have studied all the other reference books, then I guess you'll be able to do it. Maybe you can, okay? Maybe you can. Chalo, moving on. And finally, my dear student, we come to Gibbs free energy. Wow, this is just going and going and going and going and going. Acha guys, I just want to tell you something else also, okay? There is one important information that I want to tell you. So here is your, this thing, right? Here is where I'm taking your session, isn't it? Here is where I'm taking your session, and as you can see that your chats are also here. Your chats are also here. Yeah. Now, if I click on the show more, then what will happen? What will happen? Here you will get a lot of information. Yeah. This is our Telegram channel where we will provide you with the notes and everything. Yes. And here there is a form also. There should be a form link. There should be a form link. Where is the form link? Okay, the form link is not there. There is supposed to be a form. Chalo, we will do one thing. In this description box, right? In this description box, there will be a form. Why will there be a form? Because we want to know that next year, how do you want our sessions to be? Okay. To plan that, or from April, what kind of sessions we should take, how is it helping you, how is it not helping you, all of these things we want to know, and that's why I would request you all, my dear student, that please do fill that form, okay, if you can. It will just take you 2 minutes of time. Yeah, it will just take you 2 minutes of time. Just fill it so that it helps us also to understand what kind of session we should take. Alright, will you all please do that? It will be added in some time, okay? It will be added in some time. Just please do that for me, okay? In fact, you will find it in a lot of other session also. Yeah, please do that, okay? Please do fill it up so that we can plan your sessions better. We also need to understand, what kind of sessions you would like. Okay? Alright, chalo. Now let's talk about Gibbs free energy. Gibbs free energy, what is it? What is it? You remember we just spoke about spontaneous and non-spontaneous and blah, blah, blah. A lot of things that we spoke about, right? So, we want to have a parameter which can predict the spontaneity of chemical reaction, right? Yes, what do we want? We want to have a system parameter which can predict the spontaneity of chemical reaction, and that was introduced by Gibbs. So that entropy calculation for the surrounding doesn't have to be carried out. So who was it who was asking me that, ma'am, why do we need different formulas? Yes, everybody wants your life to be simple. Everybody wants our life to be simple, which is why now we have the Gibbs free energy. So Gibbs free energy mathematically is basically G is equal to H minus Ts. Okay, it is G is equal to H minus Ts. Now, if you write it for the initial state, it will be G1 is equal to H1 minus T1. Obviously, 1 is always considered to be initial. And then for the final state is equal to G2 is equal to H2 minus H2 minus Ts2. Just subtract it, you will get H2 minus H1 minus Ts2 minus 1. Now, this gives you delta G is equal to delta H minus T delta S, which is your Gibbs-Helmholtz equation. This is your Gibbs-Helmholtz equation, and this is important. Yes. Moving on from here. Now, here are different, what can the convention, what can the sign be, what is the condition, and what is delta G, and what is basically is it spontaneous or not. These values are here. So, you can just check, take a look at it. If delta H is negative, then it is favorable. T delta S, if it is positive, favorable. conditions, any condition, delta G is negative, so spontaneous. Delta H, if it is negative, it is favorable. T delta S, if it is negative, unfavorable. So here what will you do? What will you see? You will see that delta H is greater than T delta S, which is basically negative, so spontaneous. Now delta H, if it is positive, unfavorable, you can see the this thing, values later on. Okay. Here also you have the sign of delta H, delta G, and delta H, delta G, delta H, and delta S predictions of spontaneity. This also, since I will give you the PDF, you will be able to do it, isn't it? Yes, the equation which gave me multiple marks, like I told you. Yes, I'll be giving you this, so you can check it out later on. Okay, you can check it out later on. Now, tell me, for the process H2O liquid, okay, becomes H2O gaseous at T is equal to 100 degrees Celsius and 1 atmospheric pressure. The correct choice is delta S system is greater than 0 and delta S surrounding is greater than 0. Delta S system is greater than 0 and delta S surrounding is less than 0. Delta S system is less than 0 and delta S surrounding is greater than 0. Or is it option D? Come on, guys. You know what? I think let's solve it. And I can see that many of you are moving away from the session. I'm not feeling that good about it, but okay. You probably have better things to do than sitting in the session, I guess. Chalega mere ko. No problem. Anyway, option B is the correct answer, guys. Option B is the correct answer, okay? Yes, moving on from here. This is how you're going to solve it. The solution is also here. Okay. Alright, tell me. Standard entropy of X2, Y2 and XY3 are 60, 40 and 50 joule per Kelvin per mole respectively. For the reaction, half X2 plus 3 by 2 Y2 is equal to XY3. Delta H is equal to minus 30 kilojoule. To be at equilibrium, the temperature will be what? Yes. Why is the AC not working? I'm feeling so hot and I'm sweating. So annoying. Nope. Okay, do we have the answer, guys? Alright, the answer is again option B, 750 Kelvin, and here is the solution that you'll be able to do it later, okay? Yes, here you will be able to do it. Thank you so much. Thank you so much, guys. Anyway, moving on from here. Acha, from here, I would like to give it to you as your DPP. Please do this, okay? From here, take it as your DPP. Please solve it from here. The solutions are also given to you, all right? The solutions are also given to you. Please do this. There are also PYQs. There are also PYQs that you can do it, okay? All right, so from here, you guys can do it on your own because it's already more than 2 hours, 40 minutes. I don't think you have any more attention. Everything that I teach you now, you can do it now. I'll give it to you. Yes, I'll give you the PDF. No, as soon as the class ends, I'll give you the PDF in Telegram channel. You can start doing it. I guess whatever I teach you now, everything will go from the top of your head. So you can do it on your own. Is that okay? Works for you? It'll be better practice for you. Works, guys? All right. So with this note, yes. No, Anant, nothing like that. Yeah, nothing like that. In fact, if you are sat for the January attempt, it has been a good practice for you. It will be almost on the similar lines. You will get to see that. Okay, it will be almost on the similar lines. Don't worry about it. It will be almost same. Yes, just study properly. That's all. Just study properly. Chalo, with this note, I think we will end the session now. It was a very, very, very long session because we had to give you so much information. But I think almost in less than 3 hours, we have still tried to complete all the, all the possibilities of questions or and a lot of information. So I hope that you understood. If you did, don't forget to like and share and subscribe to the channel. But if there was anything that you did not understand, you can always write it in the comment section so that I can solve it for you. Alright, and I'll be giving you this PDF in the Telegram channel. You know the Telegram channel link is in the description box. Please try to solve it on your own. The solutions are also there. If you cannot solve it, only then watch the solution. Otherwise, don't. Okay? Chalo, bye-bye everybody. See ya. Have a nice day ahead. I will also see you at 8 p.m. I have another session at 8 p.m. So I'll see you then. Okay? Chalo, bye.